In this video, I'm going to talk about one of my, it's not my most favorite type of math, but it's definitely grown on me over the years and how useful it is. Dimensional analysis, is simply a way of canceling out units in order to get from point A to point B. Okay, and it all boils down to the fact that if I have something on top, that's not what I need. I need a pencil. There we go. If I have something on top and I divide by something in the bottom, they cancel out. And they cancel out in the same values, right? So I have one at the bottom, I have two at the top, so this becomes A. Well, this works with not kilograms. It will work with kilograms, but it also works with units. So if I have 1 kilogram, and I know that I have, for every 1 kilogram, I have 1,000 grams, the kilograms cancel out with one another, and I'm left with grams. From there, I can multiply across the top and divide by everything on the bottom. So one of my kind of things I always suggest students to do is to build a roadmap. Whenever you're doing this. In other words, you're starting at A, you're trying to get to C somehow. Okay? Now how can I get from A to C? Well, I don't know. So I do know that I can go from B to C, and I figured out that I can go from A to B. So you build a roadmap, and gradually it'll end up, helping you write things out. If you have numbers present, like concentration units, like percentages, write them as ratios. Because this might not mean anything to you, especially whenever you're panicking during a test. But if you write it as 6.0 moles of HCl per 1 liter solution, maybe that will help you realize that you need to use that. You don't always have to work left to right. You can go, like I said, start with C or start with A and kind of figure out where you need to go. Ratios are quantitative relationships that are true no matter who's on top, but you just got to make sure that it stays in that correct ratio. So for example, let's say I have a density of 1.28 grams per milliliter. And by the way, when you see this like this, what this is effectively saying is this value is attached to the top, and then there's a 1 at the bottom. So this is 1.28 grams per 1 milliliter. I could also say I have 1 milliliter per every 1.28 grams. So let's try this out. I need to find my volume of sulfuric acid solution. Okay, an important note. Present in a car battery containing 8 pounds of solution. So I'm starting at solution, and I'm trying to get, we'll say pounds of solution, and I'm trying to get somehow to gallons of solution. So I have density, which is a mass per volume, which means some point in time I'm probably going to go through density, right? Because I'm in mass and I need volume. So this is in grams per milliliter. This is in gallons. So somehow I'm going to have to get the liters, and then I can get the gallons. Over on this side, I need to get the grams, and then I can go through density. So let's write this out. Let's see here. I have 0.800 pounds, okay, of solution. I like to do a dimensional analysis grid. I don't care if for some reason I've heard there's like hate on the dimensional analysis grid. It's like, shut up. All right, I like my grid. So for every 1 pound, I have 453.59 grams. And then now I can use my density. So for every 1.28 grams, I have 1 milliliter. For every 1,000 mils, I have a liter. And then for every 3.785 liters, I have 1 gallon of solution. Check my units. Pounds cancel, grams cancel, milliliters cancel, liters cancel, and with gallons of solution. Multiply across the top, divide by the bottom. and I have 0.0749 grams of solution. This number right here being the one that dictates. So I recommend when you're approaching problems like this, use highlighters. Highlight the important parts. When you're working the problem, write units. At a minimum, I need to see milliliters and liters and all that stuff, because I'll take points off if you don't write that. What I'm talking about is abbreviate if you have to, but the chemicals. Okay? So how I have solution here. Because we're going to see a problem in a minute where that distinction can be the difference between a right and a wrong answer. When it comes to... let me, before I talk about that real quick, just start. Don't sit around and stare at the problem. Start trying to build a roadmap, and then start writing. Your brain has a tendency to react quite a bit better and figure things out when it's working instead of just staring at your screen or your paper or whatever. So what I was going to say earlier is that I've posted up in Canvas a PDF that unfortunately was written by a now deceased chemistry instructor. He died at a young age. It's really sad, but his approach to word problems is great. I highly recommend reading that. It's underneath your Unit 1 materials. Definitely take a look. Now, not only are we going to have to do dimensional analysis, we're also going to have to use some algebra. Okay? You can do this as part of the dimensional analysis. You could stop at the dimensional analysis and use the algebra as a separate part, or vice versa. It's math is math is math, which is what's beautiful. As long as you do it right, it's okay. So the general volume equation is that volume is equal to A times H, where this is the area times height. This becomes important, and we're going to use it several times. So kind of get that into your head. The area of a cube is its length times length, because it's all the same, so that's L cubed. These two together could be said to be A. So this is, just once again, V is equal to A times H. The volume of a sphere is equal to volume is equal to 4/3 pi r cubed. And finally, we have the area of a prism, right? So we have, this is a prism, right? So we have that and then like that. Cool. So that's a triangle, right? We can kind of think of this as a height. So basically, volume is equal to the area of a triangle times height, which is, or length if you want to call it that. Put an L there. So this is basically 1/2 base times height. So this whole thing is, or we can call it X. I think I'll call it X. I like calling it X. Let's do that. So this is volume is equal to 1/2 base times height times X or L. The reason why I changed this is because these two are not equal. Okay, this is the height over here. So let's try it out. Let's think a minute. So we have an oil tanker that develops a leak. 32.0 kilograms of crude oil leak into the ocean every minute. If oil leaking out over the course of exactly 2 days covers an area of 0.0550 miles squared, how thick in millimeters will the oil slick be? So basically, what I have is some shape, and it has an area, and it's equal to 0.0550 miles squared. What I'm trying to find out is how thick that layer will be. So I'm trying to look for this H or X or L or whatever makes you most comfortable. Okay. So that means at some point in time, I'm going to have to take my equation here, and I'm going to have to manipulate it. You got to get good at manipulating equations. Just practice. So X is equal to V over A. Okay. So I can use this. I could solve for V and I can solve for A, put them in, and get out X. All right, that's totally a legitimate way. I'm going to kind of work through a different way too. Or, well, not two, but a different way, just to kind of show you how this can be used for dimensional analysis. So let's think about what I got. I got 2 days, right? And this is something to look for in ratios. If it says every minute or every something or per something, what that is saying is 32.0 kilograms per minute. That's a ratio. Write it out. I have my time. So maybe I do, let's try days. And I'm trying to get to millimeters height or X or whatever you want to call it. Okay. Just to stay with the same thing, I'll say millimeters X. So if I go from days to minutes, I can go from using that rate, I can go to kilograms. Okay, that's nice, but that's not a unit of length. This is a unit of mass. It should start clicking into my head anytime that I see that I have a unit of mass and I'm trying to get to a unit of length or volume, that I'm going to use density. So if I use density by going first through, I'll go ahead and just write this out because you guys might not have seen this kind of stuff before. I'll go to grams using my normal metric to metric. And then using density, I'll get to milliliters. This is a volume. So I already have my area here. I could get my volume and solve to that. What I'm going to do is a little bit more conversion and then use my V over A to get to this. All right, so step one. I'm going to convert my miles squared to millimeters squared. Reason being is because I'm already, I want to have my answer in millimeters, so I might as well just get into millimeters. Actually, I lied. I'm going to get into centimeters. Let's do centimeters, and I'll show you why here in a minute. So the first thing I'm going to do is miles squared to centimeters squared. So I have 0.0550 miles squared. I have miles to feet, so for every 1 mile, I have 5,280 feet. But this isn't true because right now, with the units canceling out, I'd have mile feet, right? So one of these would cancel out, leaving me with miles, and then miles times feet is mile feet. So this, I got to square the whole thing. So make sure you do that. You will be a big factor off if you don't with these kind of things. Now that I'm in feet, I can go from every 1 foot, it's 12 inches, square that. And for every 1 inch, I have 2.54 centimeters squared. Okay, so I multiply across the top, divide by the bottom, so that's 0.0550 times 5280 squared times 12 squared times 2.54 squared. And I end up getting let's see here, 1.424, let's see here, 3 sig fig, 4 sig figs. So I'm going to need 1, 2, 3, 4. So we'll add 4 onto there. That's my last sig fig. Times 10 to the 9 centimeters squared. All right, so now I have my area, or excuse me, my area. I need my volume, so let's get the volume. So I have 2 days. That's a counted number. It's exact, so we don't use it for sig figs. For every 1 day, I have 24 hours. For every 1 hour, I have 60 minutes. For every 1 minute, I dump 32.0 kilograms into the ocean. For every 1 kilogram, I have 1,000 grams. And now I can use my density. So for every 0.905 grams, I have 1 milliliter of oil. Now, this is why I stayed in centimeters squared for the other one. You should know this from Chem 4, but just in case you don't, get it into your head now. For every 1 milliliter, I have 1 cc. 1 cc is equal to 1 cubic centimeter. So for every 1 milliliter, I have 1 cubic centimeter. Okay. Now, what I can do here is I could solve this and then take my volume and divide it by my area. What I'm going to do is I'm just going to add that as part of the problem. So I have 1.4244 times 10 to the 9, excuse me, let me zoom out, centimeters squared. Let's take a look at what the units are going to be before I punch in my answer, because I want to be in millimeters. So days are going to cancel out days, hours with hours, minutes with minutes, kilograms with kilograms, grams with grams, milliliters with milliliters. Centimeters cubed will become centimeters. So now what I'm going to do is I'm going to add one more dimension to my dimensional analysis. For every 1 centimeter, I have 10 millimeters. Now, all I got to do is multiply across the top, divide by the bottom. So I have 2 times 24 times 60 times 32 times 1,000 times 10 divided by 1, divided by 1, divided by 1, divided by 0.905, then divided by my area. And I end up getting, let's see here, 1, 2, 3, 1, 2, 3, 4, 3 sig figs, 0.715 millimeters. It's a lot of work. Okay, you could break it up into chunks if you want to. Technically, if I really wanted to, I could have started and just ran that whole thing across and done one-dimensional analysis. Okay, it's important to be able to kind of figure out how these ratios are linked and how you can use them to manipulate one another. So on this next part of the video, I'm going to talk about percentages, which is another way that we can use information in dimensional analysis. So let's talk about percents and concentrations. So percents can be treated as a ratio. Percent, right? That means per 100. So it's whatever this number is per 100. So this is 100 whatever per 100 total. So for example, if I got 65% on an exam, that means I got 65 points out of 100 points. Sometimes we use percentages for solutions. Remember that a solution is equal to the solute plus the solvent. And usually these guys, until we get to molarity, are going to be given to you as percents, but it's going to have this MV, What this is mass solute per mass solution. This is mass solute per volume solution. And this is volume solute per volume of solution. And so if I had something like this right here and I wanted to get it into a percent, I would take my 65 points divided by my 100 points total times 100, and I end up getting 65%. It's the same thing for these guys. So let's write these as a ratio. Okay, you got to be able to write these as a ratio. So I have tin in bronze, right? Because bronze is an alloy of tin and copper. So that means for every 10 grams of tin, I have 100 grams of bronze, the mixture, the total. Ethanol is drinking alcohol. So I have by volume, which is this volume per volume. If it says by mass, we're talking about this. If it's by volume, it's this. Mass over volume will be specifically stated. So that means, let's see here, I have 40 milliliters of ethanol per 100 milliliters of solution. And then finally I have 35 grams of sulfuric acid per 100 milliliters of solution. All right, now let's try using this in a dimensional analysis problem. Okay, so what volume in gallons of sulfuric acid solution? Okay, this is where I was talking about that you need to be careful. Sulfuric acid and sulfuric acid solution are not the same thing. Sulfuric acid solution will have water in it, okay, and it'll make up a portion of that total. Sulfuric acid, on the other hand, is just pure sulfuric acid. So I need to know what volume in gallons will provide 0.8 pounds of sulfuric acid. So I'm trying to go from pounds of sulfuric acid all the way to gallons of solution. Notice the difference. These are not the same thing. And notice that this density is associated with the solution. Okay, so this is an important. This is grams solution per milliliters of solution. This is why I recommend that you write out these units like this so that you can see that and get it into your head. Oh, hey, this is not the same thing. Okay. So I'll go from probably density. And somehow or another, I'm probably going to have to get into grams. Right? But I'm not going to be able to go from grams to density like we did with the previous problem. Instead, I'm going to use the percent. And I'll show you how we're going to do that. So I have 0.800 pounds of SA. First thing I'm going to do is convert into grams. So for every 1 pound, I have 453.59 grams of SA. Now I'm going to go into my percentage. So this says that 35.0 grams of SA per 100 grams of solution. Cool. I have grams of SA. I'm trying to get into grams or into something of solution, so that's beneficial to me. So now I'm going to actually that copies it. Never mind. All right, well, here we go. This is going to be a little raggedy, but that'll be fine. So for every 35.0 grams of SA, I have 100 grams of solution. I'm running out of space, so what I'm going to do is I'm going to just draw an arrow here and continue on. So now I have grams of solution on top. I need to get into gallons of solution, so now I'm going to use the density. So 1.28 grams of solution to 1 milliliter solution, 1,000 milliliters in 1 liter solution, and then for every 3.785 liters, I get 1 gallon of solution. Now I'm going to multiply these guys and these guys, okay, because I ran out of room, and then I'll divide by these ones down here. Okay. All right, so I take my 0.8 times 453.59 times 100 times 1 times 1 times 1 divided by 35 divided by 1.28 divided by 1,000 divided by 3.785, and I end up getting 0.214 gallons of solution. Oop, that looks like grams. There we go. Gallons of solution. In your homework, there's a lot of difficult problems. You need to not look at the answer key and just try them and then figure out where your errors are, because sooner or later you're going to have to do this on your own. It's going to be tough, okay? Chem 1A is not Chem 4. We do a lot in here. It's going to be difficult. Chem 4 was to prep you for this. So if you need to, go back and refresh on your stuff. Okay? Watch my other videos on the math stuff. I made math-specific stuff so that you can go back and review. Do lots and lots of practice. There's plenty out there. If you run out of practice from your workbook, then go into your Petrucci book. There's great problems in there.